Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will review everything you need to know for the upcoming test on rational and irrational numbers. So our number system that you know is the real numbers. Every number you know is a real number. So real numbers are divided sort of into two parts. The rationals, which we call Q, and the irrationals. You read this as not Q. So rational numbers is a set. It contains all fractions with integers, all terminating in recurring decimals, and all integers. So all whole numbers like -3, they are rational. All terminating decimals like 0.8, you guessed it, rational. Any recurring decimal like 0.32 recurring is rational. Now remember, any fraction with integers, that means an integer numerator and an integer denominator, it is always rational. So something like 7/13 is rational. If we want to write that a number's rational, we use this notation here. This is mathematical shorthand that says 7/3 is an element of the set Q, or simply 7/13 is a rational number. So irrational numbers are not terminating or recurring decimals. They have decimals that go forever and for which there is no pattern. So to come up with such numbers, we look at surds, square root of non-perfect squares, or the cube root of non-perfect cubes, and so on. So for example, the square root of 5 is irrational. 5 is not a perfect square, so square root of 5 is irrational. 10 is not a perfect cube. Now 10 is rational, but the cube root of 10 is irrational because 10 is not a perfect cube. Both of these have decimals that go forever and for which there is no pattern. The number pi, 3.14159 and so on, it is irrational. Now, the sum and product of a rational and irrational number is irrational. So numbers like pi plus 1, numbers like 3 times pi, they are irrational. Root 2, for example, is irrational, so that means 2 times root 2 would be irrational. And if we want to write that with mathematical notation, we write is an element of, and this time we're going to write not Q. So this says 2 root 2 is not a rational number, or it is an irrational number. Now I just want you to be careful with surds, because it's not the case that every time you see a root sign the number's irrational. So for example, something like root 36, I'm going to write over here, it's rational, because 36 is a perfect square. In fact, root 36 is just 6, and 6, being a whole number, is rational. So our real number line is the same number line you've learned since you were very young. And in this number line is all the rational and irrational numbers. We usually mark it out with whole numbers like this, but the rational numbers fit here too. So for example, the square root of 2 is about 1.41. So it would lie on the number line about here, just less than halfway between 1 and 2. And you could do that for any irrational number. So the point here, though, is root 2 doesn't equal 1.41. It's approximately equal to. 1.41 is called a rational approximation of root 2. 1.41 is rational. It's a terminating decimal. And we often use rational numbers to approximate irrational numbers when we're doing maths. All right, let's now look at using rational and irrational numbers in solving equations. So we need to first understand this table. So this says if you perform the two operations between a rational and irrational number, then you always get a rational answer. So that's what I mean when I put just an R there. If you perform operations with rational and irrational, then you always get an irrational answer. And of course, irrational and rational, it doesn't really matter the order in which you, like, say, add or multiply things, so you get an irrational answer. Now, if you get an irrational and irrational together, then there's no clear-cut answer. Sometimes you get a rational number, sometimes you get an irrational number. So to illustrate that, for example, let's say you have root 2 plus negative root 2. So this is irrational, but when you add them together you get 0, and 0 is clearly rational. On the other hand, if you do something like root 2 plus pi, that is an irrational number. That's what I mean by sometimes when you add or multiply or subtract two irrational numbers, sometimes you get rational answer, sometimes you get an irrational answer. Now, I just want to point out there is one exception to this, and that's division by 0. If you divide a rational number by 0, even though 0 is rational, you don't get a rational answer, you get an error. But other than that, if you perform any of the 4 operations with 2 rational numbers, the answer is rational. And that's because rational numbers can be written as fractions with integers. If you add, subtract, multiply, or divide 2 fractions, you get another fraction as long as you're not dividing by 0. So if I were to solve an equation like this, notice that these linear equations, so there's no power of the x there, these linear equations are always solved using the 4 basic operations. So for that reason, for this equation, we can tell without solving it, we will get a rational answer because all these numbers are rational. And when I solve it, all I'm going to be doing is performing the 4 basic operations with these numbers. Now, even though this equation looks scary, you solve it in the same way. So what we would do first is add 0.2 to both sides, and you can get your calculator to do the work. Sorry, I forgot the x there. And now if I wanted to get x by itself, instead of timesing by 0.8 recurring, I'm going to divide by 0.8 recurring. So if we put that on our calculator, we get 1.06875. This is a terminating decimal, and therefore it is rational, as we suspected. On the other hand, were I to solve this equation, I get an irrational answer. See, there's only one irrational number here, and again, to solve this equation, because it's linear, we're just going to use the 4 operations. If you use the 4 operations with rational and irrational numbers, the answer's always irrational. So to solve this equation, first thing I would do is subtract 4 from both sides, and then I would divide each side by root 2. Now, it doesn't matter if you don't really understand this, but negative 2 divided by root 2 is just negative root 2. And we already established up here that that is an irrational number. So the way we'd write it as Q naught. Okay, so when you have a linear equation and all the numbers are rational, your answer is always rational, but that's not true if you have coefficients or numbers in the equation that are irrational. All right, let's now look at rational and irrational numbers in geometry. So one area in geometry in which rational and irrational numbers come up is Pythagoras' theorem, which you would be familiar with. But just a quick recap, Pythagoras' theorem concerns right-angled triangles like this, where the largest angle is 90 degrees. So we call A and B the shorter side, C the hypotenuse, the longer side always facing the right angle. So Pythagoras' theorem says this, it says shorter side squared plus shorter side squared equals longer side squared. That works in any right-angled triangle. So we can rearrange this formula to write these. So this is the formula you use when finding a longer side. This is the one you use when finding a shorter side. You add when finding longer side and subtract when finding the shorter side. So if I wanted to find x in this right-angled triangle here, I would use this formula here because I'm finding the longer side. So x would simply be the square root of 4 squared plus 4 squared. Now 4 squared plus 4 squared is 32. X equals the square root of 32. This is called the exact answer. It's not been rounded, it's not been approximated. If we round it to say 2 decimal places, it's about 5.66. That is not the exact answer, it's a rational approximation. It's very close to root 32, but not exactly there. So Pythagoras' theorem also allows us to construct line segments that have irrational lengths, like root 13. So how would I do that? We'll find 2 square numbers that add to 13. So hopefully you can see that it's 9 and 4. There aren't really many square numbers less than 13. So root 13 is equal to the square root of 9, which is 3 squared, plus 4, which is 2 squared. What does all this mean? Well, Pythagoras theorem means I can draw a triangle like this where one side is 2, one side is 3. If I make sure that these are at right angles to each other, Pythagoras theorem tells me that this line here, which I can now draw, will have length exactly root 13. So root 13 is what is known as a constructible number because you can draw a line segment with that length. It turns out that you can draw a line segment whose length is the square root of any rational number. Square root of 0.5, square root of 207, you can draw it. All right, let's now look at a further example of where irrational numbers come up in geometry. So we've already seen that they come up when we're dealing with circles. Why is that? Because we introduced the number pi. So here is a circle with diameter 10. Now you should already know that the area of a circle is pi r squared. If the diameter is 10, the radius is 5. So the area of this circle is pi times 5 squared. So pi times 5 squared, exact answer is 25 pi. That is the exact area. If you put it on your calculator to 2 decimal places, it's about 78.54. So 78.54 is a rational approximation to the area of this circle. Its exact answer is 25 pi, which is irrational. And if you have an integer, a whole number length for the diameter or radius, then you will always get an irrational answer for the circumference or area of a circle, because irrational numbers show up in geometry all the time. Now, not only is this a rational approximation, for a long time before they had calculators, they used rational approximations to pi. See, pi is irrational. It can't be written as a fraction with an integer numerator and denominator. But there are some fractions that get damn close. So the fraction, for example, 355 over 113, that's like 3.14159. Now, its decimal thereafter diverges from that of pi, but it's very close. This is a rational number that is a pretty good approximation to pi. Well, let's see how good it is. See, the exact area of this circle is 25 pi. If I use the rational approximation here for the area, I'd get pi, which is being approximated as 355 over 113, times 5 squared. So I would get for the area 8875 over 113. Now this gets me damn close to the area. If I put that in the calculator, I get 78.5398, and it goes on. It's actually a recurring decimal. So that's very close. Now let's check how close it is. We're going to calculate the percentage error, which I know you love doing. So first we calculate the absolute error. So the absolute error is the absolute value of what we got with our approximation minus the true area. So the true area exactly is 25 pi. Now on the bottom, when we're finding the percent error, so that's the absolute error, but then we divide by the true measurement, 25 pi, and then we times by 100 and stick a percent sign on our answer. So if we actually put that on our calculator, we get a very small number. 0.50 and then an 8%. The area here, the error in the area is very low as a percentage, and this would be acceptable for most cases. So not only do irrational numbers come up everywhere in geometry, so do rational approximations to irrational numbers. All right, let's look at one more example. So it turns out the area of a regular octagon can be found using this formula. So an octagon is just a shape that has 8 sides. Regular means all sides and angles are the same size. So this formula here is involving an irrational number, root 2. So because of what we learned before about when you operate with a rational and an irrational number, if you have a rational side length, this will always give you an irrational area. So for example, if the side length was 10, then the area of this, so in exact form, all I'm going to do is replace s squared with 10 squared. So we can expand the brackets here. 2 times 100 is 200. 200 times 1 is 200. 200 times root 2 is 200 root 2. This is the exact area of a regular octagon whose side length is 10. So of course we could also find the side length if we knew the area. What I'm going to do to show that, we're going to rearrange this formula and make S the subject. It may look very difficult, but it's actually really easy. See, this is where a lot of people get mixed up with irrational numbers. 2 outside of 1 plus root 2 is actually just a number. So it's probably about 4.83 or something, but it's just a number. So if I want to get s squared by itself, I can just take a and divide by this number. So a divided by 1 plus root 2 with 2 outside equals s squared. And of course, if I want to get s by itself, I just simply square root both sides. So this is a formula allowing me to find the side length if I know the area. So if I know that the area is, let's say, 100, then the side length is just going to be 100 divided by 2 outside of 1 plus root 2, and then square root the lot. So if I put that into my calculator, I actually get about 4.71. So 4.71 is a rational number. It's a rational approximation. It is not the exact side length. Every time we represent an irrational number, we approximate it with a rational number, we're introducing a slight error into our calculations. Now we saw with the example with the circle that sometimes that error is very, very small. Sometimes the error will be above the level of tolerance. It will be a real problem. And there's been heaps of incidents in human history where very small errors have led to catastrophes. All right, thank you so much for tuning into this video. Best of luck studying, but you will ace it. This has been the luckiest maths teacher in the world. Have a great day.